Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through work 1 for chemical structure and bonding. So this has been given to you to do independently, and hopefully after I given back your work, you'll be able to watch these work tutorials and you'll be able to do your own corrections, which you are expected to do. Independent reading, independent corrections. Now that you're in O-level or IGCSE, this is typically what is expected at this stage in preparation for what is coming next when you go on to do A-levels and of course university as well. So seawater contains water and dissolved salt. So obviously seawater is a bit salty because of dissolved salt in the water itself. So salts can be extracted from seawater by taking away the water. That means we evaporate off the water and we get the solid salt remaining. So these are the names and the formula of some salts in seawater. So at this stage we haven't really done a lot of chemical formula, but looking at the formula, I hope you can appreciate that lithium is a group 1 metal and therefore is a Li+, and fluorine is a group 17 element, sorry, group 7 element with 7 outer shells, and this is fluorite with IDE, so it's actually F-, and to balance out the charges, the overall compound has no charge, but it contains ions which are charged. It has one of each because, well, the lithium atom loses 1 electron, one fluorine atom gains 1 electron, so one of each. Give you lithium fluorite. Calcium is a group 2 metal, calcium 2+. Chlorine is from group 7, it will form Cl- ion, but here you have a 2+ and a -1. When you think about the lowest common multiple, it's going to be 2, so you need to transfer 2 electron. You transfer the electron from metal to non-metal. This metal atom loses 2 electron. You need to transfer 2 electrons, so you just need 1 of it. This non-metal atom gains 1 electron for each of the non-metal atom. You need to transfer 2 electrons, so altogether you must gain 2 electrons. So this is a charge that is fixed by the position in the periodic table, because now it has fully filled outer shell electron. So its outer shell is completely filled with electrons now, therefore I need 2 of it. That's why I get the formula CaCl2. You should be getting a lot faster with these things after all, okay? Sulfate is what you call a polyatomic. Poly means many, atomic, well, it has many atoms. Is one of those in the table that you are expected to know, because you also have these in practical as well. So you need to know sulfate is SO4 2-. There's no easy way around it. So with Na+, you need, if you have 1 of these, you need 2 of these to balance out the charge. That's why you have 2 Na+ and 1 of the SO4 2-. Enough on formula. We'll deal with more about formula in the next few weeks when school reopen. Anyway, so this diagram represents 3-dimensional arrangement of ions in one of the salt, and they say it can only be used to represent one of the salts in the table. Which one? And explain your answer. If you look at the rest of the ions, this is cation is to anion 1:1, cation is to anion 1:2, cation is to anion 2 cation 1 anion. So the cation and anions are in the ratio of 2:1 or 1:2 here, but this is 1:1. Okay, so the only one which is different is going to be the lithium fluorite. So it has to be lithium fluorite, because from the diagram above, from the diagram shown above, I hope you can appreciate that this is 3-dimensional. Each cation is surrounded by 1, 2, 3, 4, 5, 6. Okay, each cation is surrounded by 6. Each cation is surrounded by 6 anions, and each anion is surrounded by, well, let's have a look at this now. If you look at one of the anions, then you will have 1, 2, 3, 4, 5. Don't forget there's a 6th one, because this is a giant ionic lattice. So it's up, down, front, back, left, right. Okay, so each anion is also surrounded by 1, 2, 3, 4, 5, 6 cation as well. Okay, so by 6 cations. Also, therefore, ratio of number, this is to do with number of cations to anions, is 6:6, which you can simplify to 1:1, and the only formula of the ions that correspond to one cation is to one anion is LiF, because these two have the cations and anion 1:2 ratio. This is 2:1 ratio for the cation is to the anion. Next question. The solid salt forms when seawater evaporates. So when the water leaves, then the solids start to form. Describe words, all right? A lot of words. The differences between the movement and arrangement of ions in the seawater, of the ions in seawater, and then the movement and arrangement of the ions in the solid salt. So first of all, if I do part 1 first, which is to do with movement, I will compare the ions in seawater. They are freely moving. The ions in the solid salt, which is an ionic compound. These are ionic compound. They have giant ionic structure. So in the solid state, the ions are not free to move around. That's why they do not conduct electricity in the solid state. But they are not asking on conduction of electricity. They're asking on movement. Okay. The ions are free or mobile to move in seawater because they are dissolved in it, all right? Meaning to say aqueous solution. But are in fixed positions, are arranged. No, there's arrangement, isn't it? Are not free to move. Are not free to move at all in the solid salt or in the solid state. Now I need to talk about arrangement. Okay, in seawater, the ions are far apart from each other. In fact, when I say free and mobile to move, I can say they are sliding over each other. Okay, so you can add the point. It's not exactly liquid. Okay, can slide past each other. Can slide to move, maybe to slide past each other. To slide past each other amongst the water molecule. Let's not do the amongst the water molecules in the seawater. So that is clear that that is referring to the what happened in the seawater. So obviously you got water around you and you have ions that are free to move and they're sliding past each other. They are not exactly liquid, they are aqueous because it's a mixture, so be very careful, yeah? But they are not free to move in the solid state. Going back to arrangement, so they are far apart from each other. With water molecules in between. With water molecules in between, because you have a lot of water. Okay. For solid salt, the ions are tightly packed. Okay, so in solid state, the particles, in this case the ions, they are tightly packed close to each other. Tightly meaning they are touching each other. Okay, tightly packed. So when seawater evaporates, water changes from liquid to gas. So this is, well, essentially is boiling, but this is to do with evaporation, which is also liquid to gas, except that evaporation takes place at any temperature, whereas boiling only takes place at boiling point. So complete the equation to show what happens when water evaporates by filling in the missing state symbol. So we have 3 state symbols: solid, liquid, and gas. So liquid going to gas. that is evaporation or boiling. So this diagram shows what happens to the molecules of water when water evaporates. So from liquid to gas, describe and explain. What happens to the bond between the atoms? So this is covalent bond, because you would have learned water is this structure with this display formula where each of these is your covalent bond. So this is the bond between the atoms, covalent bond, and the forces between the molecules. So between this molecule, there is intermolecular forces. Alright, when you did stats on matter topic, when we did heating curve and cooling curve, we talk about the interparticle forces of attractions. In reality, between molecules, we call these intermolecular forces of attraction between the molecules. So I need to talk about both of them. So let's start. Maybe I don't want to do 1 and 2 there. I'll just do between the atoms and between the molecules. Okay. So when water evaporates, the water molecules remain as H2O molecule. You could see the diagram. There is no breaking of the covalent bond because each water molecule is still 1 oxygen and 2 hydrogen. Okay, so the covalent bond, so the covalent bonds between the atoms, between the hydrogen and the oxygen atoms, remain. Okay, they are not broken or whatever. Okay, however, as the molecules move further apart, as you know, these intermolecular forces are what held the liquid molecules together, and because you want to go into gaseous state where the particles are very far apart, so you need to separate the particles. Therefore, you need to break or overcome these intermolecular forces. Okay, the intermolecular forces, the intermolecular forces of attraction. Intermolecular means between the molecules, need to be overcome, meaning you need to break it, need to be broken, okay, with the supply of energy, which is heat energy. Okay, during evaporation. It's the same thing during boiling as well, except that for boiling, which take place at one fixed temperature, because pure substance have a fixed boiling point, evaporation can take place at any temperature, but that is why not all the molecules are entirely separated, because not all the molecules are given enough energy for them to completely separate from each other. Okay, that's why evaporation can take place at any temperature, but it does not necessarily affect every single molecule of the liquid. Next question. The periodic table is arranged in groups, so I hope you know they are group 1 all the way to group 8, Roman numeral. Draw a dot and cross to show the bonding in lithium fluorite. Show all the electrons. Sometimes question doesn't say show outer shell electrons. That is when you must show all electrons. If a question says show all electrons, then you show all the electrons. When the question doesn't say that and it specifies valence electrons or valence shell, then you only draw valence shell. Okay, so lithium fluorite is going to be Li plus and F minus. Lithium is the third element in the periodic table. When it forms Li plus, it's going to have helium electronic configuration. It does not become helium because it's still element number 3 with the same proton number of 3, but it has lesser electron. Fluorine, when it gains 1 electron, is going to have neon electronic configuration. It remains as fluorine, but it becomes an ion by gaining an electron. Now it has the same electronic configuration as neon. Okay, so lithium is just going to have 2 electrons because it lost the 1 electron in the second shell. This is now going to have a plus. Don't forget your charges, because otherwise it's just an atom. Now fluorine has a first shell which is 2 electrons, and now it's an ion, so I'll draw 7. Oops, hang on, I should really use dot and cross, right? So if I already draw more cross here, so I'll use dot here. But if I had chosen to remain this as cross, then I need to change each of these to dot. Okay, not a big problem there. So I've got 7. 1, 2, 3, 4, 5, 6, 7. Group 7 has 7 outer shell electrons because this is fluorine, group 7. I gain 1 electron, so I have one of these circle, dot, and then I am F minus. I show all the inner shell because I show all the electrons. Lithium fluoride, 1 lithium atom loses 1 electron, 1 fluorine atom gain 1 electrons. The charges balance out, so I just need one of these to balance out the charge for one of these. Okay, explain why lithium fluoride conducts electricity when molten but not as a solid. Okay, so there are 2 things to say about what happened when it's molten, what happened when it's a solid. So be careful to explain fully. Okay, when molten means solid turn to liquid, that is at melting point. Okay, solid turn to liquid, melting point. When molten, the ions, meaning to say Li plus and F minus, are free to move around because now they can slide past each other. They are no longer just vibrating about fixed position. They are free to move and therefore can conduct electricity. Okay, however, in the solid state, we know in the solid state, the ions only vibrate about their fixed position. Again, the idea is their fixed position. So they are not free to move at all. And if they are not free to move, that means they are not mobile, therefore cannot conduct electricity. Alright, so to conduct electricity, you need the ions to be freely moving. So free to move is the same as mobile. So you can use the ions, not the electrons. The ions are mobile, the ions are free to move. Okay, state one other physical. Okay, so they already talked about electrical conductivity. In your syllabus, you also learned that ionic compound has high melting and boiling point. Okay, because you need to break very strong ionic bond between the oppositely charged ions, Li plus and F minus. Question 3, this is the last bit of this work 1. It's actually meant to be an essay question, that's why it's 8 mark. It's actually a free response questions. It trains you to think about what is actually going on. Okay, so there's a lot going on in this question because this is a metal, this is an element, but it's also a molecule. Okay, so this is referring to the iodine, whereas this one is an ionic compound formed between a metal and a non-metal. So this is going to be Na plus, sodium in group 1 form Na plus, iodine in group 7 form I minus, and then this is a metal. Metal is also an element. Okay, metals are element because they only contain one type of atoms and their properties are of metals. So giant metallic structure, simple molecular structure, giant ionic structure. So you can see how different this is. Yeah, okay, so state the type of bonding present, explain the nature of the attractive forces, so essentially what is holding them together and therefore what you need to break in order to react them. This is not melting or boiling, this is to do with reaction. Okay, briefly explain why the melting point of iodine is much lower than sodium iodide. Explain also in terms of electrons. Sorry, that should be part 3, this should be part 4. So quite a lot of things to answer, yeah. Anyway, so the melting point there is very low. Respectively means the first value belongs to the first one in the previous statement. The second value belongs to the second one in the previous statement. So this is NaI, and this is referring to I2. So all the group 7 elements that exist as Cl2, F2, Br2, I2, and so on and so forth. Okay, so let's get started. I've already broken it down into different sections, and this is what you do when you read question. You break it down into things you can digest. All right, so I have sodium plus iodine giving you sodium iodide. This is actually a balanced chemical equation. Sorry, this is not a balanced chemical equation because this is I2 and I cannot change the identity of it. That means there's 2 iodine atoms, and this again is the formula for ionic compound, so I cannot change the identity. That's why there is 2 in front of the NaI in order to give me 2 sodium atom on the right hand side to balance the 2 sodium atom on the left hand side, because I have 1 times 2 equal to 2 times 1. So 2 sodium now give me 2 sodium. This is a balanced equation. You will learn more about this in the next topic on stoichiometry and the mole concept. Alright, so what was the first thing again they asked? State the type of bonding for each of these substances. State the type of bonding present. So bonding present. Sodium is giant metallic structure. So this is giant metallic structure. Bonding is going to be metallic bond. I like free response question actually, because you can do a lot of thinking around it rather than one question, one answer, and it's not really training you to think deeply about a lot of concept jumbled together. So simple molecular structure means that you have iodine, covalent bond. Of course, you draw chlorine, fluorine. Why is iodine different when they're in the same group? Okay, NaI, you have Na plus and I minus. So you have giant ionic structure and you have ionic bond. So this is actually what they want for each of the substance, and I've just listed them, so that one is done. The nature of the attractive forces holding each solid together. Alright, so that is part 1. Nature of the electrostatic force of attraction. So what sort of lattice particles are present inside the structure? Okay, sodium. So the lattice particle. You need to think about every single chemical bond is electrostatic force attraction between something positive and something negative. So this is a metal, giant metallic structure. It's between sodium plus, which is the cations, and the C of delocalized valence electrons. So metals only delocalize their outermost shell electrons, meaning their valence electrons, and you become cations, positively charged and its own electrons. This is not anions, this is electrons with the cations. Therefore, it's still an element because there's no anion, there's nothing else. Okay, so the lattice particle tells you the attraction between something and something. All right, and the other one was iodine. Okay, so the lattice particle is going to be the covalent bond is the electrostatic force of attraction between the positive nuclei. So you have iodine and iodine. In the middle, you have the nucleus in the core of an atom, and then here you have the bonding electrons. Electrons are negatively charged. The nucleus has protons, which are positively charged. Okay, so between the positively charged nuclei, and the bonding electrons shared between the two nuclei. Again, this is just definition of each of these bonds. Okay, but iodine also has another bond, but this is not an interatomic bond. This is interatomic between the atom. The other one is a intermolecular force. intermolecular forces of attraction between between the iodine molecules. Okay, I should probably add one more page. I think I'm running out of page here. Oh, okay, actually I have one more page here. That's all right. So what happened next is, this is part 2. I still have, actually I think I have enough space to finish off sodium iodide. So this is the force of attraction between oppositely charged ions. And here you have Na plus from group 1 and you have I minus from group 7. Oppositely charged ions are attracted towards each other, and you get them as a result of transfer of electrons from the metal, which lose the electrons, to the non-metal, which gain the electron. Okay. Now part 2, briefly explain why iodine has a lower melting point than sodium iodide. We can relate that to structure iodine to sodium iodide. Here you need to break only the weak intermolecular force, not the covalent bond. For sodium iodide, you need to break the strong ionic bond between the oppositely charged ions. Okay, so iodine has simple molecular structure. So simple molecular structure means you have covalent bond, but you also have intermolecular forces between the molecules. So for melting, we need to break weak intermolecular forces. We have to specify exactly what we need to break. These are the kind of essay questions that you can definitely prepare for, but you need to apply in the context of the question. Okay, weak intermolecular forces of attraction between the iodine molecules. Okay, and then NaI, sodium iodide, has a giant versus simple molecular structure. So melting NaI requires breaking strong ionic bond, and your ionic bond is between oppositely charged ions, that is Na plus and I minus. I'm just writing them down in order to put it in the context of the question. What are the ions present? Okay, so that explains the melting point bit. And the last bit was in terms of electrons, how the reaction between sodium and iodine occurs. So the sodium will lose electrons and the iodine will gain the electrons. Okay, so you can either show a diagram. Okay, so I don't know, showing outermost or valence shell only. I mean, it's easier if I show the diagram. That is not a good circle at all. 1 outermost shell electrons, 2 at 1. This is going to be iodine. So I show the outermost shell electron only. 1, 2, 3, 4, 5, 6, 7. So it's got 7 valence electrons. I do not want to confuse you because electronic configuration iodine is quite long and complicated. I will just write 7 valence electron because it's in group 7. This is in group 1. Okay, so what it does is transfer of electrons. So sodium loses 1 electrons, iodine gains 1 electrons, and what you get then is sodium. Because you lost the outermost shell electrons, then you are left with the second shell, but now you are ions. And don't forget, when you have ions, you must also show the other pair, which if I just draw the outermost shell, it's just iodine with 7 dots, but I must have 1 cross because the one iodine atom gains 1 electron from the sodium atom to give me iodide ion. This is iodine atom, this is iodide ion. This is sodium atom, this is sodium ion. Alright, so this is sodium iodide. Okay, so I've just shown you iodine atom, but what actually reacts is iodine molecule. So what must happen what must happen is the iodine molecule has to break up into the atom, and once it becomes an atom, then the sodium will react with the atom itself to give you this via the transfer of electrons. But obviously it started out as a molecule, so a chemical reaction involves breaking all chemical bonds and then forming new chemical bond. So what do we break here? We need to break the metallic bond. We need to break the covalent bond, because we are not doing melting or boiling, we are doing chemical reaction. So we need to break the covalent bond, and then we can get the transfer of electrons from the metal to the non-metal, giving us the ionic compound, because we are forming ionic bond between the oppositely charged ion, Na plus and I minus. Okay, so that's it for this tutorial video on work 1, and I'll see you guys in the next video. If you got any questions, feel free to ask me when you see me in school, or drop me comments or whatever if you are not from my school. And yeah, don't forget to subscribe, follow, and share the channel, okay, at ptet.chemistry. And see you guys in the next video. Thank you for watching.